Okay. This was a good combination kind of a question, number 9 here. Definitely circular path. So I started out in number 9 by saying, okay, magnetic force is what's pushing me in a circle. Hopefully that part you could come to, you could get to. Magnetic force on a charge is Q V B. That's going to equal M V squared over R. Yay! The V cancels. They want me to get the mass of an electron. Okay, to get the M by itself. I'm hoping, Josh, you got this far. You said times by R divided by V. Is that okay so far? So I get this. The mass is going to be Q B R over V. Do I know Q? It's an electron. 1.6 times 10 to negative 19. Do I know B? Teslas. Do I know R? Yep. Do I know how fast this is traveling? No. What else have they told me in this question? Well, they've told me the accelerating voltage. This is a parallel plate question. This is where we said that QV equals a half m little v squared. This is where if you knew the charge and how many volts you sent it through, you could calculate how fast it's traveling. So far, so good? Okay. I'm going to get an expression here for V, for little v. It's going to be Q big V times 2 divided by M equals V squared. Okay? And now this is far tougher than I'm going to ask. I assign this every year and I hum and haw whether I should. Clay, what do I have right here? What do I have down here? Now I could square root. Dealing with square roots is yucky. You guys learn, I think in Math 11, that to solve a square root equation, you can square both sides. What I'm going to do is this, 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 and that, which mathematically is allowable. I squared everything. Why? Because now I can put this in for V squared. Okay? So far, so good? When I do that, I'm going to get phi. M squared equals Q squared, B squared, R squared, all over 2Q big V over M. Now I've got a fraction on the bottom. How do I divide by a fraction? It's the same as multiplying by the reciprocals. So instead of dividing by 2QV over M, I'm going to times it by M over 2Q big V. Happens. Yay. Yeah? Oh, that M cancels with this M if you divide it over. So, B squared, R squared over 2. I'm not going to give you one that tough, but it's doable. What is fair game is recognizing that I don't need to give you the speed if I tell you how many volts the charge went through. That is fair game, because that's a nice review of Unit 6 of electrostatics, or whatever unit it was. The parallel plate with the charge going through it. Is that okay, Josh? Yep. That should get you there. I haven't crunched it, but that should get you there. I hope. Let's look at some cool applications. I forgot. Cool applications. The first one is, they got them all, Manny? Yep. Trav, you with me? Yep. Okay. The cathode ray tube, the old style of TV revisited. We realized during the invention of the television that a much better way, remember it was the cathode ray tube sent electrons between plates and you deflected the electrons and you could pinpoint where you wanted it to hit the screen and it would make the screen fluoresce for a split second, glow, and from the other end, looking from the TV end, you saw an image appear. We realized very quickly a better way that didn't require as much sticking out the back to deflect the electrons. Instead of using long parallel plates, why not use magnets? Because they'll deflect electrons too. Why not use solenoids? Because we can really control the magnetic field. So in actuality, we don't use parallel plates to deflect electrons in a cathode ray tube. Instead, we use solenoids. Here is a three-dimensional diagram. Okay. And we're going to start out looking at solenoid M. Now, coming out of the page towards us are electrons. We don't deal with electrons. Electrons coming out of the page towards us is the same as protons going which way? So in a while, we're going to start pointing our thumbs into the page. But here is a solenoid, solenoid M. I'd like to see if I can figure out which way the magnetic field right here from solenoid M is. Well, I can figure it out. I got to think about it. Let me zoom way in here. There's the solenoid. Now, I know your diagram isn't great, but it seems to me, Alex, if I look at my picture, the current is going over the top towards the right. Is that correct? So I'd like all of you to imagine holding the solenoid. You can either hold it this way or this way. Hold it in such a way that your fingers are matching the current. Let's see. For me, I have to hold it this way, not this way. This way would have my fingers coming back towards me. I can't hold it this way. I have to hold it with my right hand this way. You guys okay with me? Where is the North Pole on this solenoid? I'm looking for a word that begins with the letter T and has 3 letters. Okay. All of you right now, and now I'm going to zoom out again. All of you right now, put a little north right there, a little south right there. That's step 1. Okay? Magnetic field lines always point from what to what? So if I draw in a magnetic field line, like this, right here, I would argue right here, it's pointing up from north to south. That's the part of the definition that takes over because we're close to a south pole. You okay with that, Clay? So my first argument is solenoid M, right where the electron beam is a magnetic field pointing straight up. Which way will this electron get deflected? We don't deal with electrons. An electron coming out of the page is the same as a proton going which way? So all of you point your right thumbs into the page. This is going to be that third rule with the handshake. Point your right thumbs into the page. Which way is the magnetic field? So I'm going to stand up. Now if you want to, again, you can put your piece of paper vertical to match my alignment. For me, my right thumb goes into the page. Magnetic field pointing up. I actually have to do this. Okay? Which way will the electron get deflected? To the right. What if I reverse the current? Which way will the electron get deflected? Now this is kind of weird. A vertical solenoid gives you a horizontal deflection of the charge. Well, actually no, it's because big boom boom. I do end up going through a 90-degree bend. A vertical solenoid now, in hindsight, I'm okay with that. So where it says M can deflect the electron, it turns out, depending on which way the current goes, in my specific example, to the right. I think, is that what we said? Yeah? Boom, boom, boom. Yeah, to the right. Flip the current, and we can easily flip the current because all TVs are plugged into alternating current. Deflect it to the left. Okay. By the way, the current flips at 60 hertz at a rate of 60 times per second. There's a reason why TVs have either a frame rate of 24 or 40 or multiples of 12 or multiples of 6. Easy flippings to do based on the current you're getting. You don't need to build in any special circuit. What about solenoid N? If I look at solenoid N, and I know it's on your diagram, it's tough to tell, but I think the current is going this way. I think if I hold solenoid N, I have to hold it this way, not this way. Sorry for those of you watching on YouTube. Which way is my thumb pointing? To the left. So I'm going to argue there's a north pole here, a south pole here. Which way is the magnetic field in the electron beam because of solenoid M? Magnetic fields point from what? From north to south. From north to south. Right there, because the north is the closest pole, the from north would dominate. The magnetic field right there is pointing to the left. The electrons coming out of the page, we don't deal with electrons. That's the same as a proton going into the page. Point your thumbs into the page. Magnetic field going to the left. Which way will this deflect the electrons? Up. Or if I flip the current, down. Solenoid N can deflect the electron up or down. I have a note here, show the little video, magnetic deflection. I showed you that last class, the way the magnet was able to warp the TV screen when you brought it in close, because that TV was an old style cathode ray tube. And nice thing, solenoids, much shorter. It lets you move the back in closer. The back doesn't have to stick out so much. So example 1 says this. An undeflected electron beam strikes the center of the cathode ray tube. Gotcha. Then we put a solenoid, and it right there, and it causes it to strike at location X. So when the solenoid is there, the electron beam is deflected which way? Down, slightly. What changes to the magnitude and the direction of the current in the solenoid would cause the electron beam to strike the screen at location Y? Well, is the deflection at location Y bigger or smaller than location X? So let's say the direction, first of all. Which way is direction Y deflected? Up. Which way is direction X deflected? How could I change the direction of the deflection? Flip what? Look. Well, X and Y are staying where they are. How can I change? How could I, instead of going down, instead of deflecting the electrons down, how could I deflect the electrons up? Your hint is in the right-hand column somewhere. Clay. So I'm going to go no, yes, no, yes. Clay, the deflection for Y, is it bigger or smaller than the deflection for X? So you think I increase the current or decrease the current? Because increasing the current, remember we said the magnetic field is going to be mu naught N times I over L. If you bump up the current, you'll get a bigger magnetic field, bigger force. Yes, yes, no, no. Dustin, which one is the correct answer? Has to be B. Again, I apologize. These are really tough diagrams for you folks to see. I'm going to zoom in on the solenoid, and I think if I zoom in on the solenoid, it looks to me like the current is going over the top to the right. Asks, okay, which way will an electron get deflected? 1, 2, 3, or 4? Let's walk through this. First, we have to figure out which way the magnetic field is from the solenoid. So I'm going to hold the solenoid in my hand. I'm going to curl my fingers, and you'll notice this time I'm not showing you how. You have to figure it out yourselves. I've got my hands tucked away. What's north on this solenoid, the top or the bottom?
Right hand, not your left hand.
You're not the only one. It happened in my other class too. Someone did this all left. Top, is that right?
Yeah.
So which way is, that's north, that's south. What direction is the magnetic field right there? Magnetic fields point from what to what? From north to south. And the reason I'm emphasizing to south is the closest pole to where the electron beam is. So the magnetic field is going to point to, there's the magnetic field right there at that location. If you want to, you can imagine it's a line that goes all the way like that. If you want to draw it in. Is that okay, Amelia? Which way are these electrons coming? Out of the page towards us? We don't deal with electrons. So which way am I going to point my thumb? Into the page. All of you point your right thumbs into the page. Extend your fingers like you're handshaking in the direction of the magnetic field. Which way is this electron going to get deflected? 1, 2, 3, or 4? By the way, I know it's either going to be 2 or 4 because I know a vertically aligned solenoid gives me a horizontal deflection and a horizontally aligned solenoid gives me a vertical deflection. So I already know it's 2 or 4. 4? Let's see. Electrons coming out, protons going in, magnetic field straight up. 4, direction 4. D. Okay. So application number 1, cathode ray tubes. You know what? There's going to be a multiple choice question on your test for a cathode ray tube. Either I'm going to tell you which way it's deflected and say, hey, what's the magnetic field direction? Or I'll make you figure out the magnetic field direction and I'll say which way would it get deflected, something like that. The cooler, and this is where you really want to focus, Jason, the cooler application, Mitchell, is the electric motor. It's the electric motor. This is how they work. Now, this is a very, very simplified electric motor. In reality, we build them differently to avoid a problem that I'm going to show you about in a second. Kohei, you with me? All right. Look at this picture here. A rigid wire loop. We have a fancy name for this. We call this, good gosh, spell it right, Mr. Duick. The armature of the motor. This is the part of the motor that spins inside the motor. Is placed in a magnetic field as shown below. What's going to happen? Well, the current is flowing this way, so draw a little arrow down there. I guess the current is going this way. And then we enter the magnetic field. Now, right here in location 1, the current is parallel to the magnetic field lines. Remember I said if they're parallel, if the line and the current, if the magnetic field lines and the current are parallel, no force. So we're going to ignore location 1. What I really want you to look at is right here, location 2. The current is making its way through the wire. Which way is the current moving in location 2? Up the page. Can all of you point your thumbs up the page? Which way is the magnetic field pointing? To the right? To the right? At location 2, what direction will this wire feel a force? You guys with me? Down. Going up. Magnetic field that way. This is going to get forced, I got to say, not down. What do we call this direction? Down is that way. What do we call this direction? 3 feet. Okay, into the page. So if you want to, draw a little arrow pointing there, and you can say F equals into the page. What about location 3? Now, it is true that the current is moving this way, but do you see the wire and the magnetic field lines are parallel? No force. What about location 4? Well, here, the current is now moving that way. Point your thumbs down the page. Magnetic field is still pointing to the right. Boom. I'm going to bend like that. Which way will location 4 feel a force? What? Clay. This is important. This is the breakthrough, loud and proud. The motor will spin. This is why electric motors can generate spin. Except this design sucks. There's a problem. This would only spin a half a turn. As soon as this wire got to this side, now it would still feel a force out of the page. As soon as location 2 got to this side, it would feel a force in. You would have this and come to a stop. So we've got to come up with a way somehow to always have the current coming down the page on the right-hand side and always have the current going up the page on the left-hand side. We've got to come up with a way to have current flow without having it permanently attached to the batteries. We've got to come up with some kind of a way, some kind of a mechanism that we can have current always flowing the same way. We have that. Okay? So, direction of magnetic force on segment 1, none. Segment 2, what did we say the direction of the force was? Into the page. Segment 3, none. Segment 4, will it rotate? Yes, but only for a split second. And if I haven't convinced you, let me show you a better diagram. This one's going to be more of a 3D looking along the end diagram. Okay? Here is a very, very simple electric motor. What we actually do is can you imagine right here a hamburger with no patty? So we have just the 2 bun halves with a gap in the middle. And we have brushes here. And so what's going to happen is the current is going to be going up the left-hand side here. This is going to, well, let's figure out the force. Current going this way, magnetic field from north to south. The left-hand side is going to get pushed into the page. The force is going to be downwards. The right-hand side is going to get pushed up, and it's going to spin. Now, when it gets halfway through its spin, this gap is going to be touching the metal contact brush. No current will flow. Its momentum will keep it spinning. Built up enough speed that it'll keep going. And when because it keeps going, just hang on, because I got I'll take questions at the very end, but I also got a nice 3D model. I have an app that'll show you this. Then this side will end up having flipped over, but because of this gap, when this side gets to here, the current is still going to be moving up on that left side. Let me show you a 3D model and animation. Okay. So let me pause right here. Actually, let's pause right here. Right now, no current is flowing. There's the gap in between these metal contact brushes. By the way, this thing here is called a split ring commutator. We'll write that word down in a little bit. But that's what allows you to guarantee, if I hit resume, so pause, current is flowing through the top, going this way, magnetic field is going down, the top is going to feel a force to the left, the bottom is going to feel a force to the right. Resume. It carries on through that gap with its own momentum. Again, even though the bottom has become the top and the top has become a bottom, that top branch is still having the current going that way, force to the left. It's still spinning in the same way. Okay? This is a very, very, very simplified electric motor. This motor has a problem. The problem with this motor is if you shut it off right now and then you try and restart it, nothing will happen because there's no net force. So modern motors, if you take apart an electric motor, you'll actually find instead of a rectangular armature, it'll actually have, if you look down the end, a 3-pronged at 120 degrees each armature. And if you run the numbers, then it's impossible for it to stop anywhere where there isn't enough of a net force to get it turning. For what it's worth. We're not going to look at that particular motor, but in case you take one apart, you'll notice there's some kind of often a little triangular arrangement. Okay? Question or comment?
They make it into a circle, right? So you have power applied all the time?
There's many different, once you understand this setup, you can go all over the place. Or you don't need the split ring commutator if you hook it up to an alternating current. then the maximum speed of your motor is just going to end up being whatever the frequency of your alternating current is, because that'll flip the current for you automatically. That's also doable. Question here. Yes? You want to stop it when there's no current? Okay. Yep. Because there's no force on it. There's no current. Right now, this is not a complete circuit because this brush is only touching the air. It's not touching that or that. And this contact brush and this contact brush aren't touching the metal at all. So no current will flow.
Why put that thing in there?
Because if we did not, okay, resume. If we did not, come on computer, there we go. With this setup here, okay, look at location 2. Which way is it feeling a force? Into the page? When it does a half a turn, location 2 is over here. Which way is it feeling a force? Still into the page. It would do a half turn and then come to a stop. It would. I need a loop, Mr. Dewick. I need a loop. Let me pause the video for a second while I go find something to make this analogy here. So the easy way to do that is with that split ring commutator, letting its momentum carry it for a split second. That'll guarantee that you always have, in this example, current flowing away from us in the top of this and flowing towards us in the bottom. We've managed from a direct current source to come up with a clever alternating current system, which we need to continue spin. Okay? Is that all right? It's a lot of right-hand rule stuff. Oh, and by the way, this magnet here, probably a solenoid. Oh, and by changing the current in the solenoid, I can change the magnetic field. I can change the strength of this external magnetic field. I can use that to control the speed. I can also control the speed by changing the current going through here. It really gives me a fine-tuned way I can really control an electric motor in great detail. Again, this is the simplified electric motor. Take some apart. You can find toy ones, especially if you have a remote control toy that's busted. Take it apart, take apart the motor and look at it. Just don't do it when it's plugged in. Yes?
Do you have one?
What? I have some old ones that I had somewhere and I put them somewhere stupid. I got to go hunting for them. I have some newer ones that I don't want to take apart because they work as well. Okay? So, read along with me. This shows you a simple one-turn coil. Oh, by the way, what we actually do is instead of an armature, we make this a solenoid and this a solenoid. So now you've got really strong magnetic forces going through this. Okay? I think this is the start of the, I got to look this up, the Tesla motor, I think. The Tesla motor that they use in the Tesla engine, it's actually a really old design. It was designed by Nikola Tesla over 100 years ago. It's a very simple design. Oh, the other nice thing about this then, as a motor, do you have an air intake? So you don't have to worry about particles getting in. You can build a sealed motor, which means electric motors really don't need servicing. That's why electric toys work so long. That's why a power drill, for example, from 15 years ago, probably will still work just fine when you plug it in. Okay? Yeah?
You would need a bearing to sit on the shaft.
Oh, you could do, yeah, but certainly, but the big thing is, the big thing for cars and contamination, the reason you need your oil change, it's two main ideas, right? It's the whole combustion, but also the air intake. You're getting gunk in there. Easily preventable. Note the split ring commutator. That's this thing right here. So when the armature makes a half turn, the split ring commutator makes the current in two halves of the coil change direction, so the magnetic force and the torque is always down on the left and up on the right. Or if you flip the current, down on the right and up on the left. Okay? This is actually nicknamed a St. Louis motor, but this type of motor was invented by Michael Faraday. Now, in an electric motor, we supply current, and out the other end we get motion. This is also a generator. Except in a generator, you supply the turning, the motion, and out this end you get current. And we'll look at generators in a couple lessons, but any motor is automatically a generator, and any electric generator is automatically an electric motor. It really just depends on how you want to run it, how you hook it up. Run direct current electric motor Java app. I think that is that one there. Yes, Mr. Yes, it is.
So how would a brushless motor work?
How would a brushless motor work?
You know,
Yeah, and that's the next step, because here you do have some friction with the brushes. I don't know, I need to look that up.
Okay.
Thank you. You've given me impetus to take that plunge. Yeah.
Well, I was just wondering because remember how like magnets used to be like a U-shape type of thing?
Yeah, those are the permanent horseshoe magnets. In real life, here's another picture. In real life, what you do is your armature is a solenoid, and these, let me go like this. So in real life, a better way, make your armature a solenoid, because that also gives you a strong magnetic field interacting with the other magnetic field, and make these solenoids.
Oh.
Yeah. And that way it's all electric, which means you all have magnets that you can turn on and off at a whim and control the strength of by just changing the current. And we've just finished our Unitron circuitry. We can change the current to pretty much whatever we want. Is that okay?
So the thing that's moving is also solenoid?
Yeah. Oh yeah, that also is. So that armature, instead of one wire, you could either make it a whole bunch of turns of wire, that's one way to do it, or actually make it a big solenoid. Okay.
Don't you get better at
So-
fixing a train then?
Here's a longer explanation you can read through, but I think my verbal one has worked. Instead, I got a couple of videos to show you and some homework. So your homework is, first of all, I probably will ask you, not on this test, but the next test, some conceptual stuff about electric motors. But for now, finish take-home quiz. Finish lesson 1 and 2. Finish ultimate review that I handed out last day, but I got a couple of cool videos to show you first.